Okay, in this video I'd like to introduce you to one of the ways that we can use circular motion. This is not the way that I would most frequently ask about circular motion, but there's a couple examples in here of using circular motion in a path that is moving vertically, unlike the ones we've seen before where an object was moving horizontally. So let me start out by reminding you that when we were talking about elevators, we said this person's experiencing a normal force pointed up and a gravitational force pointed down, and when the normal force and the gravitational force are unequal, we have acceleration up or down. If normal force is greater than gravity, then our person accelerates upward. If normal force is less than gravity, our person accelerates downward. And when they're equal, the person has no acceleration in the y direction and is at some sort of constant velocity in the y direction, possibly being 0 meters per second, because 0 is a constant, so that, it doesn't have to be 0, but it's some constant. Well, the same thing is going to apply for a situation like this. If you have this motorcyclist riding over a top of a hill, and the top of the hill is circular for at least part of the path, then what you have is at the very top, the normal force is acting straight upwards and the gravitational force is acting straight downwards. And so at the very top of the circle, it makes an interesting point to be able to analyze what's happening right here. At the top of the circle, if the normal force is greater than the is greater than the gravitational force, then that person is still accelerating upward. If at the top of the hill the normal force is less than the gravitational force, then they're accelerating downward. And I could tell by looking at this drawing, this person's coming over the top of the hill. I would expect that their path is going to move down as they move forward. They're going to accelerate downward, which means the normal force should be less than the gravitational force at the top of the hill. And that's why if you go over a hill very quickly in a vehicle, you get that sensation, that little moment of feeling a little bit like you're falling, actually. That sensation in your stomach. That's what that is a sensation that you're falling, because the normal force supporting you is less than the gravitational force pulling down on you. And you feel a little bit heavier if you go racing through the bottom of a path, like at the bottom of the hill here, because in that moment the normal force has to push up on you harder than the gravitational force is pulling down in order to provide you with the upward acceleration to make you stop moving downward and start moving upward. The fact that you're moving forward on the road simultaneously makes this not the simplest thing to recognize. That's why it goes at the end of the semester and not at the beginning of the semester. The way we would look at something like this is, so for example, the net force, we would analyze the normal force is pointed upwards and the gravity is pointed downwards, but this then ends up being a little bit strange, because what direction is the acceleration? The acceleration at the top of the circle is pointed toward the middle of the circle. That's the part we really want to make sure that we're clear about. So the way a question like this might be worded is something like this. This motorcyclist is riding over the top of this hill. The top of the hill is approximates a circle for at least part of the path there. How fast does this person have to be going so that they just barely leave the road at the very, very top of the hill? They lose contact with the road just for the briefest of moments, just at the top of the hill. They give us the effective radius of the circular path there is 15 meters. So the way that we would approach this is we would say, well, this person is not actually going in a full circle, but in that moment their motion is circular. We can just say that the net force is equal to ma, and we can say that the normal force is pointed in a positive y direction and gravitational force is pointed in a negative y direction, and their motion is going to follow circular motion, but we can specifically say that the centripetal acceleration here is pointed in what we've defined as a negative y direction. We can then say Newton's second law tells us that the net force is ma, and we know that the a is v squared over r because it's approximating circular motion here. We also know the net force is the normal force pointed up minus gravity pointed down, and so we have our negative on the right side also because our acceleration is in the negative direction. Now, does that negative go with the mass or the v or the r? It actually doesn't really matter as long as we recognize that the acceleration has to be in the exact same direction as the net force. In this problem, they want to know how fast we have to be going. So we're solving for V in order for the tires to lose contact with the road, which means the normal force goes to 0. So we're going to substitute in 0 for the normal force, and we're going to say that what that leaves us with is the force of gravity is providing that centripetal acceleration. The mass is the same on both sides. That's the mass of the motorcyclist and motorcycle combined. So I wind up being able to say that the speed is therefore the square root of g times the radius of the circle. At the very, very top of the circle, if this person is traveling 12.1 meters per second, they will just barely have the normal force reach 0 newtons. Meaning if they're going any faster than this, they'll actually lose contact with the road, at least briefly. So another way to look at a situation like this is, what if you have a situation where you actually are moving in a circle the whole time? For example, like this. If I have a string that's spinning around and making an object go in a circle, in a previous video we had an image with a woman swinging a bucket of water around in a horizontal circle. And so in that horizontal circle, the centripetal force was the x component of the tension. Here, the tension is sometimes pulling up and sometimes pulling down, while gravity's always pulling down. So this is a more complicated scenario, and that's really what I'm trying to get at, is vertical circles are a more complicated scenario than horizontal circles, because the net force on the object that's moving in the circle actually changes throughout the circle, and probably the speed of the object changes too. And so we don't really want to do a lot of analysis of these. They just get really complicated. The best place to have to analyze one of these, and therefore the place that I would be most likely to ask you to analyze one of these, is the top of the circle or the bottom of the circle. These are the two best places. And the reason for that is that at the top of the circle, as you see here, the tension force and the gravitational force are both pulling down on my object. They're working together, and I can just add them. At the bottom of the circle, they're working exactly opposite each other, and I can add them where I say one's positive and one's negative. And I don't want to overcomplicate what's positive and what's negative. So the way that I would do a problem like this is, if I was dealing with the top of the circle, I would add the tension force and the gravitational force together, and I would get some number of newtons that is my net force, and then without bothering to worry about whether that was positive or negative, I would say that the net force, by definition, has to be in the same direction as the acceleration, so I can go straight into F equals ma. At the bottom of the circle, I can kind of do the same thing after I've added the forces together. So I would maybe say tension is positive and gravity is negative, and add those two together and get a net force. And once I have my net force, I can go straight into F equals ma without having to worry about negatives. It's not that you don't care about negatives. It's that whether or not the negative is there for the net force, it would have to be the exact same sign as it is for the acceleration. So for a vertical circle, if you're analyzing only the top or only the bottom moment, you can treat the Newton's second law aspect of it as absolute values. But the vectors themselves, you definitely have to account for whether they're in the same direction or the opposite. So in this particular question, they give us the mass of the ball, 0.150 kilograms, and it's on the end of a 1.10 meter long string or cord. The cord has no mass, and it's swung in a vertical circle. And I would know it's a vertical circle because in a question it would specifically say vertical circle, or because you would see something visual like in the next problem. But it won't be a secret. Determine the minimum speed the ball must have at the top of the arc so the ball continues moving in a circle. So this should, the previous question with the motorcycle should maybe give us a little bit of a hint. And the basic idea here is that I want to start with Newton's second law as usual and say that the net force equals ma, and the A will be centripetal, and the net force at the top of the circle will be the force of gravity and the force of tension in the same direction. You can call them both positive or both negative, it doesn't really matter. Their combined force is the net force that will equal m times the centripetal acceleration. So I can say the tension plus the gravity are working together at the top of the circle. So I don't need to, if I'm calling one of them negative, I need to call both of them negative and the acceleration negative. So either make them all positive or make all the forces and accelerations negative at the top of the circle because they're all pointed toward the middle of the circle. The tension force would be 0 when to achieve the minimum speed. The tension force can't be less than 0. And the tension force is contributing to the net force that's contributing to this acceleration, that's contributing to this speed in a circular motion. So the way to minimize V, I can't alter the gravitational force. The way to minimize V at the top of the circle is to bring the tension all the way to 0. So much like the previous problem, we want to know what happens if the tension becomes 0 just briefly, just at that instant at the top of the circle. And what that means is V squared equals mg times r over m. And the m will divide out, and I will wind up that the minimum speed at the top of the circle is the square root of gr. So I get 3.28 meters per second in this particular problem. But that square root of gr should look familiar. We've seen that before. Okay, and I want to emphasize that previous problem could be reproduced with a different type of force instead of tension, and the process would be the exact same. So for example, if we were to talk about a vehicle moving through a loop-the-loop, in order for this vehicle to make it through this circular loop, it has to have enough speed so that at the top of the circle it is either still in contact with the road, so it still has a normal force, or the normal force reaches 0 only at the very, very, very top of the circle. And it looks like right here they just about made it. Someone sent me this entertaining Photoshop, and I thought, oh, well, of course, if I'm teaching a physics class, I'm going to turn this into a question. So how fast would you have to be going, assuming that there's no air resistance at all? How fast would you have to be going at the bottom of the loop in order for you to make it all the way through the loop, drive all the way through this loop without losing contact like on the previous slide? And we're going to make an estimate here that if a car lane is about 3 meters wide, which is about right, then I estimate that this loop is about 60 meters in diameter. And I need to know that because we need the radius. So the radius is therefore 30 meters. I'm going to solve this with a little bit of conservation of energy. I'm going to say that the energy at the bottom of the loop is kinetic, and at the top of the loop it's going to be gravitational but also kinetic. So at my gravitational potential energy at the bottom will be 0. So 1/2 m v bottom squared, and v bottom is what I'm looking for, equals 1/2 v top squared plus mg delta y at the top. And our delta y at the top will be that we're 60 meters up, and our v at the top is something that we have solved in a couple times here. The minimum speed to get through the circle is the square root of gr. So at the top of the circle, our normal force would just barely touch 0. To find our minimum speed, we're going to wind up with this square root of gr. So students frequently ask, like, oh, should I just memorize that the minimum speed to go through the circle is gr? And I'm very hesitant to say yes, because you have to make sure that you are remembering when that is and is not appropriate. So if you throw that root gr into some horizontal circle question or some satellite orbit question where it's not appropriate, then that doesn't do you any good. So be cautious. But in this particular case, the minimum speed at the top of the circle is the square root of gr, which I get to be 17.1 meters per second, which I then substitute in for the speed at the top. And I went ahead and changed those subscripts from C to top because that was driving me nuts. So the mass divides out all the way across because I don't know what kind of car you're driving. And because the mass shows up in every term, so 1/2 speed at the bottom squared equals 1/2 speed at the top squared, which has to be at least 17.1 meters per second, plus our g delta y. And our delta y, of course, is that we are a full diameter up 60 meters. So I calculate that your speed at the bottom, if you have no air resistance, and this assumes you're just coasting through, I guess, and not revving the engine. But this says that you have to be going 38.3 meters per second at the bottom loop, which is 85 miles an hour, which doesn't seem that much. Well, I'm never going to get a chance to try it. I'm going to trust the math. That's the last example I have. The point of that was to emphasize that the vertical circle with an object going through a loop-to-loop, the car driving through a loop-to-loop, was the exact same question, really, as the vertical circle with the ball on the string. So if the circle is vertical, the question that you would get asked is something like, what is the force necessary at the bottom of the circle if the mass of the object is this and the speed is that? Or what is the minimum speed necessary at the top? And now you know that if you're asked about the minimum speed to make it through the circular motion, you know that the gravitational force is there, but the other force becomes zero at that very top moment. That's how you solve for that. Okay, that was the last example for this video. So let me be done.